Okay, so welcome to the first lecture of week 8. And last time we had been discussing the algebra of limits, and we proved the following theorem that if you have two convergent sequences and you take the term-wise sum of these two, then that new sequence is also convergent and the limit is the sum of the old limits. And if you take the term-wise product of these two sequences, so this new sequence, that's also convergent and the limit is the product of the limits. And then using this statement 2, we derived two more corollaries, namely that if you scale a sequence, a convergent sequence by a fixed real number, then that new sequence is also convergent and the limit is the scaled limit by the same number. And if you, for a fixed k, a natural number, take the kth power of each of the terms, okay, so the term-wise kth power, then that new sequence is also convergent and the limit is the kth power of the limit of the old sequence. And we had mentioned that there are two more statements which we didn't prove last time. So let's begin today's lecture with by proving these two statements. So let me recall what the statements were. One says that if you take the term-wise absolute value, then that new sequence is convergent and the limit of this new sequence is the absolute value of the old limit. And the second statement says that if you have a sequence, each of whose terms are non-zero, so that I can take the reciprocals of these terms and look at that new sequence, then if the old sequence has a limit which is non-zero, then this new sequence is convergent, and in fact the limit of this new sequence, the term-wise reciprocals, that is equal to the reciprocal of the old limit. Okay, so these are the two things that we want to show. Let's begin with statement number 5, namely that if I take the term-wise absolute value, then this new sequence is convergent with limit being the absolute value of the old limit. So what we want to show is, given any epsilon positive, there exists an index such that beyond that index, the distance of the nth term, which is mod an, to the limit, which is mod a, should be made smaller than epsilon. Now, well, this combination reminds us of the reverse triangle inequality, which we had met long ago in chapter 1, which says that the mod of the difference between the mods of two real numbers is less than or equal to the mod of the difference between the two real numbers. So because of that, this mod of mod an minus mod a is less than or equal to mod an minus a. And of course, this can be made small if I go far enough out in the sequence, because the sequence an converges to its limit, which we have denoted by a. So we have a plan for the proof, so let's carry it out. So let epsilon be positive, and then we know that there exists an index capital N such that beyond that index, the distance of the nth term of our original sequence to its limit is less than epsilon. So now with the same capital N, for all n's which are bigger than capital N, the distance of the nth term of the new sequence, which is mod an minus mod a, thanks to the reverse triangle inequality, is less than or equal to mod an minus a, which we know is less than epsilon. So given the epsilon positive, we have produced a capital N such that beyond that n, the distance of the nth term to the limit is smaller than epsilon. In other words, the limit as n tends to infinity of mod an is equal to mod a, and a was the old limit, so it's mod of the old limit. So that proves statement number 5. And now let's see what statement number 6 was. That said that if you have a convergent sequence, all the terms of which are non-zero and the limit is also non-zero, then the reciprocal, term-wise reciprocal sequence is convergent and the limit is the reciprocal of the old limit. Okay, first of all, I want to point out that this condition that the limit of the original sequence is non-zero is not superfluous. And here is an example. If I take the sequence Bn as 1 by n, okay, then we know that this sequence converges to 0. Also, each of the terms Bn, which is 1 by n, is non-zero. So I can look at the reciprocal, term-wise reciprocal sequence, which is 1 divided by 1 by n, which is n, the sequence of natural numbers. Now this sequence is clearly not convergent, because we know that the sequence of natural numbers is not bounded by the Archimedean property. So since it's not bounded, it cannot be convergent, because every convergent sequence has got to be bounded, right? So since this is not bounded, it cannot be convergent. So the conclusion does not seem to hold. So what went wrong? What went wrong was that the original sequence, although each of the terms was non-zero, the limit was in fact zero. Okay, whereas our statement is saying that only when the limit is non-zero are we assured that this new sequence is convergent, and the limit is then the reciprocal of the old limit, which makes sense because this is non-zero, so 1 divided by non-zero is a legitimate real number. So this condition cannot be dropped, and now let's prove this sixth statement of this theorem. So let's do some rough work first. So let me call the limit of this original sequence Bn, which is a non-zero number, as B. So B is a non-zero number. And what do we want to prove? We want to make sure that the nth term of our new sequence, the reciprocal sequence, so that's 1 by Bn, its distance to the claimed limit, which is 1 by the old limit, so that's 1 by B, that we should be able to make small, this distance, if you go far enough out in the sequence. So if I do some algebra, you get B minus Bn divided by Bnb, right? And the mod of the product of two numbers is the product of the two mods. So using that, we get that you get the mod of the numerator divided by the mod of the denominator, and the mod of the denominator further splits into mod Bn times mod B. Now let's look at the numerator. There you have mod of B minus Bn, which is the same as mod of Bn minus B, because mod of minus x is the same as mod x. And we know that since Bn converges to B, this distance can be made small. Mod B is just a constant, so that's harmless. But what might trouble us is 1 divided by mod Bn, because if that grows, then we are in trouble, because although this is small, because this is growing, maybe the combination of the two might grow and prevent this from being small. Okay. So in order to prove that this distance can be made small, we have to have some control on 1 by mod Bn. If we manage to show that that stays bounded with n for all large n's, then we are in business, because we know that this is small and then this is essentially, these are constants. Okay, or they have a bound, a constant bound. So the question is, can we bound 1 by mod Bn? In other words, does there exist a positive m such that 1 by mod Bn is less than or equal to m for all large n's? Now, a rearrangement of this is that mod Bn is bigger than or equal to 1 by m. Okay, so in other words, the real question is, can I bound mod Bn from below by a positive number? Okay, because then I can take the reciprocal and then essentially I have a bound for 1 by mod Bn. Now, how could we prove this? Well, the only thing I know is that Bn gets close to B for large n's. So I know that given any positive epsilon, which we leave undetermined for now, and soon we'll choose a concrete epsilon. But if we had an epsilon, then I know that the distance of Bn to B can be made smaller than epsilon, and somehow from here I have to deduce a lower positive bound for mod Bn. Well, what comes to mind, where does mod Bn come by itself with arbitrary signs, is in the reverse triangle inequality, because we know that this is certainly bigger than or equal to mod of mod Bn minus B, and this is bigger than or equal to both mod Bn minus B and the minus of that. So you also get mod B minus mod Bn. And this latter thing is great, because you see, if I bring mod Bn over to the other side, I get something exactly resembling this. Mod Bn is bigger than or equal to something. And what's the something? Well, it's mod B minus epsilon. So if the epsilon was small at the outset, so that this combination stays positive, we have got our bound, right? So for example, if I choose epsilon, so mod B is a positive number. Why? Because B is non-zero, so the mod of that will be a positive number. So if I choose epsilon equal to mod B by 2, which is a positive number, then I'll be guaranteed this for large n's. And essentially this would mean that we are guaranteed this for large n's, where the epsilon is mod B by 2, and these two combine to give mod B by 2, which is a positive number. So if I think of this as 1 by m, by rearranging, I've got my estimate that 1 by mod Bn is less than or equal to m, where the m is the reciprocal of this one. Okay, so somehow the convergence of Bn to this non-zero number is giving us the bound on the reciprocal of mod Bn, and then we are in business, because we know that this is small and this is bounded above by m, and so this whole combination can be made smaller than any challenged epsilon. The task is to look at 1 by mod Bn minus 1 by b and make sure that this is small. That's the distance of the nth term of our new sequence to the limit. Well, that by algebra we have seen is this, and that's less than or equal to this thing, and now we know that 1 by mod Bn, that can be made smaller than 2 by mod b for large enough n's, having chosen this epsilon to be equal to mod b by 2. Okay, and then you also have this 1 by mod b factor, and now the question is, how small should I make this so that the whole combination is less than epsilon? Well, if I make this smaller than epsilon mod b square by 2, then this mod b square will cancel against this, the 2 will cancel, leaving neatly an epsilon. Okay, so in order to find the index, there are two steps involved. One is to get the lower bound on mod Bn, which is positive, or in other words, the upper bound on 1 by mod Bn. For that, we have to choose epsilon equal to mod b by 2, use the convergence of Bn to b, and to get this bound. The second step is to make this small. So that's the plan. Okay. So now that we have a plan, let's write down the proof carefully. Okay. So let epsilon be positive. That's given to us. And now I take epsilon prime as the minimum of these two things. So I take epsilon mod b square by 2 and mod b by 2. Okay, so both of these are positive numbers. The minimum of these two positive numbers is also positive, and that I call as epsilon prime. Okay, and let's recall that b was the limit. Okay, now choose the capital N, so that for every little n larger than this capital N, the distance of Bn to b is less than epsilon prime. Okay, now when this happens, then basically this is that magical index which ensures that both this as well as this latter thing happen. Why? Because epsilon prime is going to be smaller than this as well as this one. Okay, so this will be satisfied with epsilon equal to mod b by 2, and also this one will be satisfied with this epsilon. Okay, so that's the idea. So we choose the capital N such that for every index bigger than this capital N, the distance of Bn to b is less than epsilon prime. So let's first make sure that our bound on mod Bn below is satisfied. So for every n which is bigger than this capital N, we know that mod b minus mod Bn is of course less than or equal to mod of mod Bn minus mod b, because minus x is less than or equal to mod x, right? And by the reverse triangle inequality, this is less than or equal to mod Bn minus b, which we know is less than epsilon prime, but epsilon prime is less than mod b by 2. So we have this thing, and by rearranging, we get mod Bn is bigger than mod b minus mod b by 2, which is mod b by 2. And hence I get that the reciprocal of mod Bn is less than 2 by mod b. Now that we have got the bound on this red stuff here, then we proceed with our rest of the proof. Now for little n larger than capital N, okay, I am looking at the nth term of our reciprocal sequence minus the limit. By algebra we know that this is mod b minus bn divided by mod bn minus b. This is the same as mod of bn minus b. Yeah, and now this 1 by mod bn, thanks to this one, is less than or equal to 2 by mod b, and then I have 1 by mod b in the denominator. Okay, that was this one. Now since n is bigger than capital N, I know that mod Bn minus b is less than epsilon prime, so this thing is less than epsilon prime, but epsilon prime is the minimum of these two, so it's less than epsilon mod b square by 2 times 2 by mod b square, so the b square, mod b square cancels, the 2 cancels, leaving an epsilon. And so we have got that given any epsilon positive, there exists a capital N. How did we choose this capital N? Well, from this epsilon, you produce this magical number epsilon prime, and then for that positive epsilon prime, there exists an index because of the convergence of the sequence Bn to B, such that beyond that index this is smaller than epsilon prime, and that then delivered us the bound as well as then our final thing, inequality, that the nth term minus the claimed limit has distance less than epsilon. So we have proved this sequence is convergent with limit 1 by b, and b was this limit of the original sequence, so this is 1 divided by the limit of the original sequence. Okay, so that proves this theorem on the algebra of limits. And now we have last time already seen a calculational example, but let me give you a slightly different example now of a different nature. And this example is on the arithmetic geometric mean. Okay, so let's first see what this is. So suppose I have two positive numbers, a and b. Okay, and that I take as the seeds of two sequences that I'm going to define recursively, the sequence an and the sequence bn. Okay, the sequence an is generated by taking the previous terms of these two sequences and taking the geometric mean, okay, of the nth terms, and the new sequence, the sequence bn, is constructed by taking the arithmetic mean of the earlier terms of these two sequences. Okay, so let's see how this works. So if my two seed numbers were 1 and root 2, okay, so this is a1 and b1, then a2 will be the the geometric mean of these two. So it will be the square root of 1 times square root of 2, which if you use your calculator, it turns out to be this one. Okay, if you b2 will be the arithmetic mean of a1 and b1, so that turns out to be in this case as this number, okay, with the calculator. So now I've got a2 and b2. Then a3 will be the geometric mean of a2 and b2, so it will be square root of a2 b2. a2 and b2 I've just calculated, well, the square root of their product turns out to be this. b3 will be the arithmetic mean of a2 and b2, so a2 plus b2 divided by 2, well, a2 and b2 are these, so their arithmetic mean turns out to be this one. Okay, now that I've got a3 and b3, a4 will be square root a3 b3, which turns out to be this, and b4 will be a3 plus b3 divided by 2, which turns out to be this. We notice something remarkable, that already a2 b2 you had that the most significant digit was matching, and 0.18 is also quite close to 0.20, right? And then in the next step we had sort of coincidence of the first 4 digits after the decimal point. You see, you have 1981 here, 1981 here also. And in the next step you have coincidence of the first 8 decimal digits. You see, 19814023, 19814023. So it seems that both of these sequences, a1, a2, a3 and so on, and b1, b2, b3 and so on, they both seem to be converging very rapidly, and moreover they seem to be converging to the same limit. So I want to show that first of all these two sequences are convergent, and that will be a good revision of what we did in the last lecture. And moreover, I want to show that they have the same limit, and over here to show that they have the same limit I'll use the algebra of limits that we have learned. Okay, so my claim is that first of all the two sequences an and bn, which are defined in this way, they converge. Secondly, they converge to a common limit, and this common limit is called the arithmetic geometric mean of the two of the seed numbers that you start with. Here of course for illustration I used 1 and root 2, but actually a1 can be any positive number and b1 is any number bigger than a1. Okay, so you can use any positive a and b1 as any b which is strictly bigger than a. And then the recursive definitions are that an plus 1 is generated from the previous terms by their geometric mean, and bn plus 1 is generated from the previous terms by taking the arithmetic mean. Okay, and the common limit of these two is then called the arithmetic geometric mean. So we want to show all these things. Okay, now in order to do this, we are going to actually show that the sequence an is increasing and bounded, and hence by the theorem that we learned from last week, namely that monotone bounded sequences are convergent, an will be convergent. And similarly, the sequence Bn we will show is decreasing, okay, and bounded. And again, by the theorem from last time, monotone bounded sequences are convergent, Bn will also be convergent. So convergence will be handled in that way. And in order to show this increasing and decreasing business, we will need the fact that the geometric mean of two positive numbers is always less than or equal to their arithmetic mean. So what I'm saying is that the square root of AB is always less than or equal to A plus B divided by 2, okay, for positive A and B. So why does this work out? Well, if you rearrange this, okay, you see you get A plus B is bigger than or equal to 2 square root of AB, yeah? And that means if I bring the 2 square root of AB to the other side, it is B minus 2 square root of AB plus A is bigger than or equal to 0. That's what we want to show. And you see this B is really square root of B square, and this A is really square root of A square. So then we recognize this combination is square root of B minus A square, and we want to show this is non-negative. Of course that's true, right? For any real number, if you square it, it's non-negative. So if you want, you can start from here. So since A and B are positive, square root of B minus square root of A is some real number, its square is non-negative. If I expand this out, you get B minus 2 square root of AB plus A is non-negative, and by rearranging this you get that the arithmetic mean is bigger than or equal to the geometric mean. So we know that the arithmetic mean always lies on the right on the number line. So here is now a pictorial representation of what's going on. We have the seed numbers A and B. A is positive, B is positive, B is bigger than A. How is the sequence generated? Well, B2 will be their arithmetic mean. What does arithmetic mean geometrically? It's just A plus B by 2, so that's where the midpoint, it's the real number corresponding to the midpoint of this line segment. The geometric mean will be smaller, so A2 will be on the left of B2. Then B3 will be the arithmetic mean of this A2 and B2, so it will be its midpoint. So that's B3 over here. Notice that B3 is somewhat smaller, and A3 will be the geometric mean of A2 and B2, but that will lie on the left of B3 because the geometric mean is less than or equal to the arithmetic mean, right? So A3 will be here. Then B4 will be the midpoint of A3 and B3, so that will be here. A4 will be slightly to the left of that, yeah. And you see that you have rapid convergence. Moreover, we visibly see that A1, A2, A3 is going to be increasing, B1, B2, B3 is going to be decreasing, and since they are sort of closing in very fast, there will be a common limit. So that's the intuitive understanding, but we have not proved anything yet. So let's prove this now, okay? So using induction on n, you can prove this, what we visibly see over here, namely that, of course, A is positive, and the sequence is increasing, so any an will be bigger than or equal to the first term, a1, which is A, and an plus 1 is bigger than an. That's what it means to say that the sequence is increasing. Each geometric mean A is less than or equal to the corresponding arithmetic mean, right? So A3 is less than or equal to B3, A2 is less than or equal to B2, and because of that, an plus 1 I'm claiming is less than or equal to bn plus 1, and the sequence B is decreasing. Bn is decreasing, so bn plus 1 is less than or equal to bn, and bn is of course then less than or equal to b1, which is b. So this whole statement holds for each n that can be shown by induction. Okay, so let's first check the base case. What's the base case? So I put n equal to 1 throughout. A is less than or equal to a1. A1 is A, so here you have equality. And A is less than or equal to A2, which will be square root of AB. So is A less than or equal to square root of AB? That's the same as saying that A is less than B, which is true. A is less than or equal to B, that's true. And then A2 is less than or equal to B2, is that true? Yeah, that's the arithmetic geometric mean inequality. Then B2 is less than or equal to B1, which is the same as saying that A plus B by 2 is less than or equal to B. That's the same as saying A is less than or equal to B, which is true. and b1 is less than or equal to L, b1 is equal to b. So here we have equality. So the base case is true. Then you assume that this whole statement, whole chain of inequality, if it is true for some n, then it's true for n plus 1. And the proof is, you almost quite similar. You just have to use the arithmetic geometric mean and these earlier induction hypothesis inequalities. So that I won't do. You can pause the video and try to do it yourself. And if you have a question regarding this, we can take it up in the question and answer session. Okay, so the sequence an is increasing because of this, and it's also bounded because, of course, an is bigger than 0 and less than or equal to b, so it's convergent. Moreover, the sequence bn is decreasing because of this inequality, and its bn is bounded because bn is less than or equal to b and bigger than a, so it's convergent. Okay, so we already know that these two sequences are convergent, but we want to show that they have a common limit. Okay, and here is where we use the algebra of limits. So suppose the sequence an has limit alpha and the sequence bn has limit beta. Now bn plus 1 is an plus bn divided by 2. And we know that this sequence, by the algebra of limits, the sequence with the nth term given by this, converges to alpha plus beta by 2. And now look at this new sequence Cn, which is given by bn plus 1. So Cn is basically the sequence b2, b3, b4 and so on. So it starts from b2 instead of b1. But of course, if the sequence b1, b2, b3 is convergent with limit beta, this sequence will also be convergent with limit beta, right? So by the uniqueness of limits, we'll get beta is equal to alpha plus beta by 2, and that will give us alpha is equal to beta. So why is this sequence b2, b3, b4 and so on also convergent with limit beta? Well, that's clear because we know that given any epsilon positive, there exists a large enough index such that beyond that index, the distance of the nth term of the sequence bn to its limit beta is smaller than epsilon. But then you take the same n, and for little n bigger than n, mod of Cn minus beta will be mod of bn plus 1 minus beta, right? But when the n is bigger than capital N, n plus 1 will also be bigger than capital N, and so this distance to beta will be smaller than epsilon. So Cn also converges with limit beta, right? So this sequence Cn converges to beta, and that's the same as this sequence, which by the algebra of limit converges to alpha plus beta by 2. And since it's one and the same sequence, by the uniqueness of limits, this beta has got to be equal to alpha plus beta by 2. In other words, 2 beta is alpha plus beta, and hence alpha is equal to beta. And this common limit is what we call the arithmetic geometric mean. In fact, this arises in several places in mathematics, and this is outside the scope of this course, but I just remark that Gauss showed that in fact this integral 1 divided by square root of x square plus a square times x square plus b square is in fact pi divided by the arithmetic geometric mean of a and b. So you see that if a and b were equal, then you would have 1 by x square plus a square, and that has a primitive which is the arctan, right? So from that you would get pi by a if a and b were equal. A and b are not the same, then you get a number in between a and b, and that's this arithmetic geometric mean. Anyway, so that's just a curious remark. So we have now finished the discussion of the algebra of limits, and the next topic that we are going to discuss is the sandwich theorem. So it's in the same theme of things that we are discussing, namely theorems to deduce the convergence of a sequence by looking at properties of the sequence. So this sandwich theorem tells us that if a sequence is sandwiched between two convergent sequences with a common limit, then in fact this sequence which is sandwiched between these two also is convergent with the same limit. Okay, so sort of pictorially, here is a sequence which is sandwiched between two sequences, both of which are converging to this limit indicated by the red line. Then this middle sequence also converges to the same thing. So sort of more precisely, if you have that the sequence an converges to L, the sequence bn converges to L, and for all indices, the sequence Cn is in between term-wise between these two sequences, right? So for all n, Cn is less than or equal to Bn and bigger than or equal to An, then this middle sequence also converges to L. So we'll now prove this theorem, which says that if An is convergent with limit L, Bn is convergent with limit L, and for all indices Cn is less than or equal to Bn and bigger than or equal to An, then this Cn is also convergent with limit L. Okay. So what do we want to show? Given any epsilon positive, we want to produce a capital N such that beyond that N, the distance of Cn to L is less than epsilon. And what do we know? We know that given this epsilon positive, there exists an index Na such that beyond that index, the distance of An to L is smaller than epsilon because An converges to L. Similarly, given this epsilon positive, there exists an index Nb such that beyond that index, mod of Bn minus L is less than epsilon. This is because Bn converges to L as well. And a third thing that we know is that for every index, Cn lies in between An and Bn. Now I want to see this combination Cn minus L. So let's subtract L on all sides. So this also says that for all n, An minus L is less than or equal to Cn minus L is less than or equal to Bn minus L. Now this Bn minus L is less than its mod, which is less than epsilon. So I know that for n bigger than Nb, this is smaller than epsilon. And it would be great if this is bigger than minus epsilon, because then I would get Cn minus L is less than epsilon and bigger than minus epsilon. In other words, this holds. So the question is this true? And the answer is yes, because you see, minus of this thing is less than or equal to its mod. Okay, so you will get minus of An minus L is less than epsilon, a rearrangement of it, which is exactly this thing. Okay, so to complete the proof, now let's set n, capital N, equal to Na plus Nb, where Na and Nb are like this. Then whenever little n is bigger than capital N is certainly bigger than Na, so that this holds, and in particular then minus An minus L is less than or equal to mod of An minus L, because minus x is less than or equal to mod x for every real x, and this is less than epsilon. And also when little n is bigger than capital N, little n is also bigger than Nb, so that Bn minus L is less than or equal to its mod, which is less than epsilon. Okay, so I've got this is less than epsilon and this is less than epsilon. So now Cn minus L, which we know thanks to this thing, is less than or equal to Bn minus epsilon, which is Bn minus L, which is less than epsilon because of this. And Cn minus L is bigger than or equal to An minus L, which is bigger than minus epsilon because of this thing, right? Because if I take this to the other side and this to this side, it is exactly this one. So I've got Cn minus L is less than epsilon and bigger than minus epsilon, but that just means that mod of Cn minus L is less than epsilon. It's equivalent, these two statements. So we have got that given any epsilon positive, we produce the capital N such that beyond that n, the distance of the nth term to the limit is less than epsilon, and so this sequence is convergent with limit L. Okay, now in this proof, we notice that it was not really essential that for every n this should hold. It was enough if this was true for all large enough n's. So the condition in the theorem, you see this condition in the theorem, for all n's this should happen, can actually be weakened to this condition, that there exists some n0 such that beyond that n0, Cn is less than or equal to Bn and bigger than or equal to An. Why? Because you see this holds for all n's bigger than Na, this holds for all n's bigger than Nb, and this thing, this middle part holds for all n's bigger than n0. So instead of taking capital N as Na plus Nb, if you take Na plus Nb plus n0, then for all little n's bigger than capital N, this is holding as well as this is holding, right? And that allows us to show that this conclusion is true, right? So the insistence that this inequality is hold for all n's was not necessary. In fact, for the first few n's it can be violated as long as it holds for all the n's beyond a certain milestone index, the proof works. Okay, so we'll use this theorem also. Okay, so let's see some examples of this sandwich theorem. So the first example I want to consider, and this is sort of a starred example in the sense that it's sort of a theorem. It says that if r is a positive number which is strictly less than 1, and I look at the sequence r square, r cube, r to power 4 and so on, so powers of r, that sequence in fact converges to 0. So to prove this, I will do the following. I'll use sandwich theorem, and to do that I'll need an estimate on r to the power n, and this estimate is obtained in a peculiar way. Okay, so let's first see the argument, and then we will understand why this is sort of quite natural. So we have a positive number which is strictly less than 1. So then if I look at 1 by r, that's a number which is bigger than 1. Okay, so if I subtract 1, I'm still left with a positive number. So let's give that a name. Let's call that h. So h is equal to 1 by r minus 1. Okay, and this is really 1 minus r by r, and so this is positive because r is positive, and since r is strictly less than 1, the numerator is also positive, so this is a positive number. So 1 by r is equal to 1 plus h. And if I look at 1 by Rn, and Rn is the quantity that I'm interested in, that is equal to 1 plus h to the power n. By the binomial theorem, this is n choose 0 plus n choose 1h plus n choose 2h square all the way up till n choose n hn. And you see each of these terms is positive. That's why having this h positive was a good idea. And moreover, we see that one of the terms is nh. So this whole sum is certainly bigger than nh. Now you might wonder, why are we doing this? The reason is because if I rearrange 1 by r is bigger than nh, I get that Rn, r to the power n, so you bring this over to that side and nh in the denominator, we see is less than 1 by nh. Now 1 by h is just a fixed number, and we know that 1 by n goes to 0. Meanwhile, Rn is always bigger than 0. So think of the constant sequence 0, 0, 0, 0, 0, and think of this sequence 1 by h, 1 by 2h, 1 by 3h, and so on, and that is converging to 0 because it's just a scaled version of 1 by n. The constant sequence 0 converges to 0, and Rn is flanked between these two. So by the sandwich theorem, we know that this middle thing also should converge to 0. So the upshot of it all is that we did this trick of looking at 1 by r minus 1, this positive number, so that we could write 1 by r as this thing, 1 plus something, and then 1 by Rn would be 1 plus something positive to the power n, which allowed us to obtain this estimate where you could get Rn is less than 1 divided by n times something. Okay, so that was a little bit of a clever trick, but it seems to work. Now, the first time you see this, it might seem out of the blue, but we will see a couple of these, and then we will see that this is not that strange. Okay, and as we get more and more experienced with analysis, we just remember that that was some trick like this, and we'll be able to reproduce it without memorization. Okay, so by the sandwich theorem, then to reiterate, the limit of this sequence is equal to 0. But what was so special about having r in between 0 and 1? Okay, so let's also look at the case what happens with some other values of r. Okay, so for example, if r is equal to 0, then you see this is just the constant sequence which is 0 always. So 0, 0, 0, that is of course convergent with limit 0. Okay, so even if r is bigger than or equal to 0, I have that the limit of this sequence is equal to 0. What about the case when r is in between minus 1 and 1? I look at this case now because I still want mod r is strictly less than 1, and it's of course always greater than or equal to 0. Now, and I want to use what I have learned so far. So you see this mod r is a new number which is bigger than or equal to 0 and strictly less than 1. So if I look at the limit of this sequence mod r to the power n, by what we have just learned, this sequence has limit 0, right? But this mod of r to the power n is the same as mod rn, yeah? Because mod of xy is the same as mod x times mod y. So if you repeatedly use this, you see this thing, that mod of r to the power n is mod r times mod r times mod r n times, so it is mod r to the power n, right? So I've got that this sequence mod r to the power n is convergent with limit 0 whenever r is in between -1 and 1. And this actually also tells me what happens with this sequence r to the power n, because again I use the sandwich theorem. You see, Rn is less than or equal to mod r to the power n, right? Because Rn is less than or equal to mod of Rn, which is the same as mod r to the power n, and I know that this sequence goes to 0. Minus r to the power n is less than or equal to mod of Rn, yeah? And if I rearrange this, I get r to the power n is bigger than or equal to minus mod r to the power n, which is the same as this one. Right? And since this is going to 0, because that's just minus of this sequence, that goes to 0, that goes to 0, so the middle thing also goes to 0 by the sandwich theorem. Okay, alright, so we also know this case. What happens if r is equal to 1? Well, then r to the power n is just the constant sequence 1, so that is of course convergent with limit 1. What happens when r is equal to -1? Then r to the power n is -1 to the power n. So that's the alternating sequence, which we have seen earlier is divergent. So in that case, you don't have convergence. And what happens if mod r is bigger than 1? Well, in that case, we sort of intuitively see that the sequence is not going to be bounded, right? Because each time you sort of scale it by a number which is bigger than 1. So it's not going to remain bounded. To sort of give a more sort of concrete proof or concrete argument, if mod r is bigger than 1, then h, which is mod r minus 1, is a positive number. So mod of r to the power n, so mod r is equal to 1 plus h to the power n, which again by the binomial theorem is 1 plus nh plus positive terms, so this is bigger than nh. So this cannot be bounded, you see, because if this was bounded, less than m, we would get that n is bounded for all natural numbers. The set of natural numbers has a bound. So that's of course absurd. So this sequence is not bounded, and so this sequence cannot be convergent. So mod r to the power n diverges, but that means that Rn also diverges, because if this were convergent, then its mod by the algebra of limits would be convergent. But we know that its mod is this one, which diverges, right? So to summarize, if I look at the sequence r to the power n, its convergence or divergence status depends on what the number r is. If r is in between -1 and 1, then it converges to 0. If r is equal to 1, it converges to 1. If r is equal to -1, it diverges, or if mod r is strictly bigger than 1, then it also diverges. Okay, so now we know what happens with this sequence or all the real numbers r. Okay, the convergence is only when r is equal to 1 or r is strictly in between -1 and 1. Alright, so this was application of the sandwich theorem, and here is an application of the result that we have just learned. Okay, so now if little r is in between -1 and 1, my claim is that this sequence, whose nth term is this partial sum 1 plus r square plus so on up till r to the power n, that is in fact convergent with the limit 1 divided by 1 minus r. And I sort of summarize this theorem by saying that the sum of the geometric series with mod r strictly less than 1 is this limit. Okay, so don't worry about what this series or sum means. It just means this statement that this sequence whose nth term is given by this is convergent. Okay, alright, so the nth term is given by 1 plus r square plus so on up till r to the power n, and this is the sum of a geometric progression. Okay, and we know how to handle this. There's this trick of multiplying the numerator and the denominator by 1 minus the common ratio. Why is that a good idea? Because the numerator that then gives a telescoping sum. What do I mean by this? Well, you see that 1 will multiply each of these, reproducing this. So you get 1 plus r square plus so on up till rn, and then minus r will also multiply these things, which will produce minuses of these things. So you'll get minus r square all the way up till minus r to the power n plus 1. And you see most of these terms cancel and only the first and the last one remain. So it's as if the last term has been brought in contact with the first one. So in that sense, it's a telescoping sum. It sort of telescopically collapses. So you have 1 minus r to the power n plus 1, which I can write as r times rn. And we know something about this sequence. Since little r is in between minus 1 and 1, this sequence, whose nth term is rn, converges to 0. And then if I scale it by minus r, that will still converge to 0. If I add to it the constant sequence 1, 1, 1, 1, 1, that will converge to 1. And then the denominator, I'm scaling it by 1 divided by 1 minus r, so the limit will get scaled. So this, the sequence whose nth term is this one, that converges with limit 1 minus r times 0 divided by 1 minus r, which is exactly 1 divided by 1 minus r. And so the sequence whose nth term is this converges to 1 divided by 1 minus r. Okay, here is now one more example of the use of the sandwich theorem. Okay, and here we will use a similar sort of advanced trick for estimation of n-Rn. Okay, so we will again sandwich it between two sequences, both of which are converging to 0. Okay. So first of all, let's read what the claim is. In this example or theorem, we are going to prove that when little r is in between 0 and 1, then the limit as n tends to infinity of n times Rn is equal to 0. I will proceed in a similar way as before. So since little r is a positive number which is strictly less than 1, its reciprocal is bigger than 1. So if I subtract 1, I get a positive number. Let's call it h. So h, which is 1 minus r by r, is positive because numerator and denominator are both positive. So 1 by Rn, and I like looking at Rn, because I have that over here. So 1 by Rn is, you see 1 by r is equal to 1 plus h, and 1 by r to the power n will be 1 plus h to the power n. By binomial theorem, this will be this thing. So it's 1 plus nh plus n choose 2, which is n times n minus 1 by 2h square plus bunch of positive terms. Now over here, if I try to mimic what I did earlier, if I just say that, well, this is bigger than nh, then you see I get, if I bring this Rn to this side, then I'll get Rn times n. That's brilliant. I see that over here. That is less than 1 by h, and on the other hand, it's bigger than 0. But 1 by h is not good enough, because 1 by h will converge to 1 by h, because h is a fixed number. Once the r has been decided, the h has been decided. So that's not good, because to apply the sandwich theorem, both of them should converge to 0, right? So that's not good. So using this estimate that this is bigger than nh is not good. But if you take the next one, n times n minus 1 divided by 2h square, then if I again bring this Rn over to this side, I get nRn, that's good. And if I bring all the rest to the other side, this n minus 1 will come in the denominator, you see. And that's a good thing, because whenever n is in the denominator and the rest is just a constant, this of course converges to 0, right? And then we can use the sandwich theorem. So the observation here is that if we mimic the earlier complicated proof, then we notice that this estimate is not going to be good. So instead we use this one, because then there is an extra n which is left, which helps us to estimate what we need to use the sandwich theorem, right? So this is certainly bigger than n times n minus 1 by 2 times h square whenever n is bigger than or equal to 2. And by rearranging, I get that, well, nRn is of course bigger than 0, but on the other hand, if I bring Rn over to this side, you get nRn is less than 2 divided by n minus 1 h square. 2 divided by n minus 1 h square for n equal to 2, 3, 4 and so on. Well, that is convergent to limit 0, and this is the constant sequence which converges to 0, so the middle thing also converges to 0. So by the sandwich theorem, this is convergent with limit 0. Despite the fact that this n is growing, this is sort of decaying exponentially fast, and the combination goes to 0. So now let's look at this example that for a is strictly bigger than 1, the limit as n tends to infinity of a to the power 1 by n is 1. In other words, the sequence a square root of a, cube root of a, and so on converges with limit 1. Now first of all, since a is strictly bigger than 1, the nth root of a is also strictly bigger than 1, because otherwise nth root of a would be less than or equal to 1, and by taking nth powers you would get a is less than or equal to 1, which is not true. And now I define hn, which is the nth root of a minus 1, which is positive because nth root of a is strictly bigger than 1. Now earlier you had just h, right, which we had taken as 1 by r minus 1, but now notice that this h depends on the n, because you see that when n is equal to 1 you would get a minus 1, when n is equal to 2 you would get square root of a minus 1, which is different than a minus 1 in general, and so on. So there is a dependence of h on n. Now to show that nth root of a has limit 1 is the same as saying that hn goes to 0. So we will use the sandwich theorem on the hn, right? And notice that the reason we introduce this is we can get an estimate on hn as follows. So nth root of a is 1 plus hn. So a is 1 plus hn to the power n, which again by the binomial theorem is 1 plus nhn plus positive terms, and this is bigger than nhn. And now we have got our estimate that hn is strictly less than a divided by n. A divided by n of course converges to 0, and hn on the other hand is always positive. So this constant sequence also converges to 0, and by sandwich theorem then hn has to converge to 0. Okay, and hence the limit as n tends to infinity of nth root of a, that is 1 plus hn, and hn goes to 0. So by the algebra of limits this converges to 1 plus 0, which is equal to 1. Why a strictly bigger than 1? Well, in fact this works also with any positive a. So first let's tackle the case when a is equal to 1. If a is equal to 1, this is just the constant sequence 1, which has of course limit 1. And if a is strictly less than 1 and positive, then you see 1 by a is bigger than 1. By the previous part, the limit as n tends to infinity of 1 by a to the power 1 by n converges to 1, and then a to the power 1 by n is just the reciprocal of this one. So this is 1 divided by 1 by a to the power 1 by n. And since this sequence we know converges to 1, right, we have that this reciprocal sequence converges with limit the reciprocal of the old limit, but the old limit was 1 and its reciprocal is 1. So we have used the algebra of limits over here. So to summarize, for any positive a, the limit as n tends to infinity of a to the power 1 by n is equal to 1. As an application, we can prove the following theorem, that if a and b are any two real numbers, then the limit as n tends to infinity of mod a to the power n plus mod b to the power n the whole to the power 1 by n is equal to the maximum of mod a and mod b. Okay, so let's call m the maximum, and again we'll use the sandwich theorem. So first of all, mod a to the power n is less than or equal to m to the power n, and mod b to the power n is less than or equal to m to the power n. So their sum is less than or equal to m to the power n plus m to the power n, which is 2 times m to the power n. So if I take the nth roots, I get the nth term of the sequence of our interest is less than or equal to 2 to the power 1 by n times m. Now 2 to the power 1 by n converges to 1 because of this thing, right? A is a equal to 2. And so this combination will converge to m. So wouldn't it be great if this is also bigger than or equal to m, because then by the sandwich theorem this middle thing would converge to m. So to get the reverse inequality, notice that m being the maximum of these two is going to be one of these two. So m to the power n will be either a to the power n or b to the power n, so each of which is certainly less than or equal to mod a to the power n plus mod b to the power n, right? And so we have this, and if I take the nth roots, then m is less than or equal to the nth root of this one. So I also got the other inequality. So I've got this nth term of the sequence of interest is less than or equal to m times 2 to the power 1 by n and bigger than or equal to m. This constant sequence m converges to m, and this sequence is a scaled version of this sequence. This sequence converges to 1, so the scaled version converges to the scaled limit, which is m times 1. And so by the Sandwich theorem, this middle thing also converges to m, which is the maximum of mod A and mod B. Alright, so as a final application of this one, I want to give sort of a geometric situation here. So in the first quadrant, so this is the xy plane, R2, here is the x-axis, here is the y-axis, and I'm just looking at the first quadrant. So x and y are both non-negative. And I look at the curve x to the power n plus y to the power n equal to 1 when n is equal to 1. Then it's just x plus y equal to 1, and that's this straight line segment lying in the first quadrant. If I take n equal to 2, x square plus y square, well, that will be equal to 1. That will be the circle with center 0, and so the first quadrant part will be this quarter circle, right? And in general, for n equal to 3, 4 and so on, sort of this looks generically like this. It will be a curve like this. And now let us take the line y equal to kx, which will meet each of these curves, and k determines the slope. So k might be sort of bigger than 1, k might be equal to 1, or k might be less than 1. And it will intersect these points, and where it intersects the curve xn plus yn equal to 1, that point I call xn yn. So this is x1 y1, this is x2 y2, xn yn in general, okay, x3 y3, x4 y4 and so on. I want to see what happens to this sequence of points. Okay, and we'll use the previous result to deduce this. So we have xn to the power n plus yn to the power n is equal to 1, and yn is equal to kxn for these points for all n. So if I substitute this in here, then I get xn to the power n plus kn xn to the power n is equal to 1. If I take xn to the power n as a common factor, I get 1 plus kn as the other factor, and that is equal to 1. If I take the nth roots, I get xn times 1 plus kn whole to the power 1 by n is equal to 1. So xn is equal to 1 by 1 plus kn whole to the power 1 by n. And we know what the limit of this is as n tends to infinity from the previous result. Okay, so indeed it converges to the maximum of 1 and k, right? So if k is bigger than 1, then this maximum is equal to k, so that this xn converges to 1 by k, and then yn, which is k times xn, the scaled version, will converge to the scaled limit, which is k times 1 by k, which is 1. So when k is bigger than 1, in other words, the line looks like this, these points seem to converge to the point 1 by k comma 1. So the y-axis, the y-coordinate is 1, so it will lie on this line. The y is k times the x-coordinate, so it lies on the line y is equal to kx. So it's the intersection of this line with this horizontal line. So it seems to converge to this point. Similarly, if k is strictly less than 1, then this maximum is equal to 1, and so the xn converges to 1. Meanwhile, the yn, being k times xn, converges to k, right? K times 1, which is equal to k. So when the slope is less than 1, then these points converge to the point 1 comma k, which lies on the line y is equal to kx, right? So that lies on this vertical line. So it seems that the points over here will always go towards this horizontal line, and the points where the slope of the line is less than 1 will always go toward. So it's as if these curves are growing towards this corner curve. Okay. Next time what we will learn is this last topic of chapter 2, which is on subsequence of a sequence, and we will also learn this very important Bolzano-Weierstrass theorem, which says that every bounded sequence has a convergent subsequence.